All right, welcome back everyone. Hope you had a good weekend. So this is lecture 16 of CS229, and today we're going to start a new chapter on unsupervised learning. Right? So unsupervised learning will be the broad topic for the rest of this week and parts of next week. And the specific topics for today are the k-means algorithm, the mixture of Gaussians, which is also called the GMM or Gaussian Mixture Models, and the expectation maximization algorithm. And jumping into today's topics, so what we've seen so far is the first few weeks, first 3-4 weeks or so, we covered supervised learning, where we were trying to learn a function that maps x to y, and we are given pairs of x, y as our training set or examples. And then after supervised learning, we went into some learning theory. We studied bias variance trade-off in the bias variance analysis and saw a little bit into generalization. And then we last week we saw reinforcement learning, where the goal in reinforcement learning is, rather than minimizing some kind of a loss function, we want to maximize the value by choosing a suitable policy, right? And here value is the long-term cumulative sum of discounted rewards, and we want to maximize the long-term reward by choosing a policy. Now the new chapter we're going to start today, starting today, is unsupervised learning. And in the unsupervised learning case, we are given a data set, generally a collection of x1, x2, etc., xn, right? And we do not have a corresponding y variable associated with each x variable. We are just given a set of examples, a set of x's, where each xi is in Rd, in a d-dimensional real space, for example. And our goal is to learn some kind of a structure in these x's, right? We don't have a corresponding correct answer. We don't have what's otherwise called supervision of what the correct answer is for each x, but in general we are just given a collection of x's, and the goal is to find some kind of an interesting structure in these x's that hopefully gives us some new insight, right? So we've seen logistic regression before, and in the case of logistic regression, x1, xd. Let me use a few colors here. We had some we were given a data set like this, and our goal was to find a separating hyperplane, right? This is supervised learning because we are given the correct answer, that is the color of each point along with the point itself, right? Whereas in the unsupervised learning, the problem would translate to something like this, right? We are given some points, just the x's, and our goal now is to learn some kind of an interesting structure here, right? Previously we had the correct answer for each input. Now we are just given a collection of x's, and a reasonable structure to find in this are these two clusters. So loosely speaking, we want to look for such structures when we are given just x's. However, this problem is generally not very well defined, right? In the first case, for each point we were told what the correct answer is, but consider a problem like this. Right? And if we are asked to find an interesting structure in this kind of a data, it would be totally reasonable to say this is one cluster, this is one cluster, and this is another cluster, right? And another totally reasonable thing would be to say this is one cluster and this is one cluster, right? So in a way there is no correct answer, so to speak, and our goal is to learn some kind of an interesting structure in the presence of such kind of ambiguities, right? The way to you want to think of this is classification problems in the supervised setting are somewhat related to clustering problems in the unsupervised setting, right? Where the cluster identity is like the class label, and we want to, looking at just the x's, find out both how many number of classes there are and also to which class each example belongs to, right? And why would this be interesting? So for example, this would be interesting, for example, for in examples where supposing you have you're working at a marketing department and you have information about your customers, right? And the information about your customers can be represented in some kind of a vector space where you have the age of the customer here, you have their annual income, and on another axis you might have their geographical location. Right? And each customer would be a point in this space. Right? And now as a person who's working in marketing, you might be interested to perform some kind of a market segmentation to identify groups of customers so that you can do some kind of a targeted advertising or marketing campaign or some such thing, right? So that's just one example of why unsupervised learning might be interesting. So the first unsupervised learning algorithm that we'll be seeing is something called as the k-means clustering algorithm. The k-means clustering algorithm is pretty straightforward. This is probably one of the simplest algorithms for unsupervised learning. K-means algorithm. So we are given a data set of n examples, x1 through xn, where each xi is in Rd, right? And our goal is to group them into k clusters, right? And for the purposes of the algorithm, we'll assume that k is given to us. And the algorithm goes like this: initialize cluster centroids mu1, mu2, mu k. So you have one centroid per cluster where each of them are in Rd randomly. Right? So each of these mu1, mu2, mu k is a vector. Previously in our notations, generally having a suffix to a variable generally meant it was a scalar, right? But in this case, mu1 is a full vector, right? And there are k such full vectors, mu1 through mu k, and we initialize them randomly, and then we repeat this until convergence. Repeat until convergence for every I, where I denotes the example number, set Ci equal to arg min j xi minus mu j square, and then that's step 1. And step 2, for every j, where j is now where j indicates the cluster identity, set mu j is equal to sum over I equals 1 to n, indicator of Ci equals j of xi and sum over I equals 1 to n indicator Ci equals j. So what are we doing here? K-means is an iterative algorithm where we are given a set of n examples which we index by I, and we want to identify k clusters where the k clusters are indexed by j. We initialize the cluster centroids randomly where mu1 through mu k are each a vector in RD, and we repeat until convergence where for every I we set Ci here. C you can think of C as an array of length n where for each example there is a corresponding Ci, for every xi there is a corresponding Ci, and we set Ci to be the identity, that's the argmin of j, identity of the nearest mean, right? And based on the set Ci vector or Ci array, we then recalculate mu j, where mu j is calculated as the mean of all xi's for which Ci equals j. Yes, question?
In practice, how do you know what k is?
So as I said already, for now let's assume k is told to us. We are given what k is, and this is the algorithm, right? And the way it's a pretty straightforward algorithm where we alternate between one step where we are calculating the cluster identities for each example, and in the other step where we are recalculating the cluster centroids. And this is probably seen through a simple visualization, which we'll have a quick look at. Any questions on this so far? Yes, question? So the question is, what happens? Can we use an unsupervised learning setting to learn the different cluster centers and use that as a classification algorithm?
Just remove all the labels and just pass it to a clustering algorithm. It will behave the same way as a supervised.
Yeah, it might or it might not behave the same way as a supervised learning algorithm. Yeah, so supposing this is, think of this as a collection of points that are given to us, where each green point is a data point in xi in RD, and the way the algorithm works like this. Here we assume k equals 2, and the red x and the blue x, you can think of them as mu1 and mu2, which are randomly initialized. And in the first step, what we do is for each point x, we identify the nearest cluster, right? We set Ci to be the identity of that cluster which has the smallest L2 distance between that point and the cluster centroid. So over here, the red dots are those for which the red x is closer, and the blue dots are those x's for which the blue x is closer, right? So this is like setting the Ci's in the first iteration. And once we set the Ci's, in the next step what we do is recalculate the mu j's. So what happened here, I'm going to go back one slide. So at this stage we set all the cluster identities, and in the next stage what we want to do is recalculate the red x, that is the mu, to be at the middle of the red points, at the red circles, and similarly recalculate the blue mu to be the center of all the blue circles, and that's what happens in the next slide over here, right? So this is just taking the mean of all the points of the corresponding color, and then what we do, we repeat and assign new cluster identities, reevaluate all the points to see which new cluster centroid they are closer to. So what happened? Let me go back one slide just to see the difference. So these 2 points, which previously belonged to the old blue centroid, now got mapped to the new to the red one, and then we reevaluate the centroids again, and the centroids will now move to the center. Right? And once we reach here, in the next iteration, I actually moved a slide. Nothing changes, and we declare that the algorithm has converged. Right? It's a pretty simple and straightforward algorithm. And now a few natural questions to ask is, will this algorithm always converge, and will it always give us the same answers all the time? Okay. So it can be shown that the algorithm does always converge, and what we mean by convergence in this algorithm has a special meaning. So if we consider this loss function called j of c comma mu to be equal to I equals 1 through n xi minus mu ci square, and this is also called the distortion function. And the k-means algorithm is basically an algorithm to minimizing this particular loss, or the distortion function, in the form of coordinate descent. So what's coordinate descent? Coordinate descent, you can think of coordinate descent as a variant of gradient descent, where what we are doing is at each step, instead of minimizing the loss with respect to all the input variables, we only minimize the loss with respect to a few variables while holding the others fixed. Right? So the step number 1 corresponds to minimizing the distortion function by holding mu fixed and optimizing c, where we calculate new c's. And step number 2 corresponds to then minimizing j again by holding the c's fixed and optimizing it with respect to mu. Right? So k-means is coordinate descent of the distortion function j, where in one step we optimize it with respect to c, and the other step we optimize it with respect to mu, and the result of the optimization results in these closed form rules for recalculating the c's and mu's. And we say that k-means algorithm converges in the sense that eventually we are going to reach some kind of a local minima of this j function. Right? It may so happen that we may have minimized j, but we may end up toggling between two sets of mu's and c's, alternating once we reach a local minima, though that happens extremely rarely in practice. But we will eventually reach a state where j is no longer minimized further. We're going to flatten out in j, and most of the times, pretty much all the time in practice, that's going to result in some kind of a mu and c that does not change anymore. This j is non-convex, which means the mu's and the c's that we end up in can change from run to run. If you start with a different initialization, you may end up with a different set of mu's and c's, right? Which kind of ties back to a question that was asked before. Why do we ever need to use the label identities and not just perform clustering? And the answer is that this is basically a non-convex problem, and we can end up with different cluster identities depending on the initialization. Any questions on this? Yes, question?
When you look at any cost function, how do you determine if it's, like, even in neural networks, how do you determine if it's convex or not?
So the question is, by looking at a function, how do we determine whether it is convex or not? In general, it is the answer is not always straightforward. So it is easy to show that something is convex by showing it as a composition of convex subfunctions. Right? However, showing something is not convex is not always that straightforward. Something could, which may not appear to be convex at first, can sometimes with some kind of reparameterization may end up being convex, etc. In this case, it happens to be non-convex. Any questions on this? Cool. So given this clustering approach that we've seen, let's move on to something that is slightly different and also somewhat related, which is the problem of density estimation. So density estimation generally refers to the problem where we are given some number of data points and this is in R, think of it as the x-axis, and these points are residing in a continuous space, right? And the goal is to now we assume that these points are sampled from some kind of a probability distribution, and because these points are coming on a continuous distribution, the corresponding probability distribution has some kind of a density. Right? It's not a probability mass function, but it's a probability density function. Right? And given these points that look like this, the question is, what is the density function from which these points were sampled? And in general, it's a very hard problem, because if you want to fit this data really, really well, then the best possible fit would be a density that looks like this, where it has, like a Dirac delta function over every data point. A peak that's really, really peaked over each data point, and you can, this is a valid density, but at the same time it doesn't feel natural, right? Another equally valid density would be something that looks like this. And this is also a valid density, right, from which it could have been sampled, because there's nothing to the left, nothing to the right, and there's some values over here, there's something where there's some data, so you might have some kind of a density. And also, this is also a valid. Right? So all these are different possible answers for what the underlying density is from which these points are calculated. And kind of the fundamental problem of density estimation is that the density function has to be a continuous function. In the case, if these were, the outcomes of coin tosses where the support was discrete, then maximum likelihood was pretty straightforward. You could, treat them as a multinomial and just count them. But whereas in density estimation, we need to come up with this smooth function over discrete observations. Right? I say discrete observations because we have a fixed number of observations, and we want to come up with a smooth estimate. So a common approach in density estimation is to use this model called the Gaussian Mixture Model, or it's also called the mixture of Gaussians. Right? The Gaussian Mixture Model, where given some data points that look like this, we make this hypothesis that there are these two underlying two different distinct Gaussian distributions. There is one Gaussian distribution from which these were sampled, another Gaussian distribution from which these were sampled, and together you can take the sum of these two Gaussian probability distributions and say this entire data set is sampled from these two different Gaussian, these two mixture of these two Gaussians. Right? And the choice of k is something again is similar to in k-means. It is something that we choose by visual inspection or in general seeing how well the data fit the number of k. And the problem we have now is to given this data set, estimate the two Gaussians from which the data set might have come. Right? We are not told what the identity of the two Gaussians are. If this were to be a supervised setting, then we would have right? They would come with some kind of an identity. And we could have fit one Gaussian here and the other here. Okay. And this is exactly what we did in, do any of you remember where we did something like this? GDA, exactly. So in GDA, we were told that X's come from are sampled from Gaussians, and there are these two different classes, class 1 and class 2. Right? And our goal was to take these X's along with their cluster identities, the corresponding Y's, and estimate the mu's and sigmas for the two classes. Right? Now, in Gaussian mixture model, we are essentially generalizing GDA in a way where we are not given what the Y labels are, we are just given the X's, and we also relax the constraint which we had in GDA that the covariance had to be the same. In this case, the covariance can be different. And our goal is to now come up with some kind of density P of x that allows us to assign probability density to the observed values. Right? So that's the setting in which the Gaussian mixture model comes into picture. And the reason why we are interested to even calculate this P of x, there are many reasons why calculating P of x could be interesting. So here's one example. So here's a completely made up example. Supposing you are an aircraft manufacturer where, let's assume the parts that we manufacture have two kind of attributes. Let's say heat tolerance, and if any of you are in aeronautics, what might be another? Let's call it heat tolerance and whatever power output, whatever that means. So let's assume there are these two kind of attributes that are there for some part that we manufacture, and in general, what we observe that if we were to plot the every manufactured part as a point here, we might observe that most of the normal parts fall along some kind of a distribution like this. Maybe there are two different kinds of subtypes of parts, maybe based on the material or something, where some of them fall in this distribution, some of them fall in this kind of a distribution. Whatever be the reason, but generally, let's assume that normal-looking parts fall in this kind of belong to this kind of a probability distribution. Now suppose we want to have some kind of an automated anomaly detection where we want to detect that some part is faulty for some reason, right? For example, a part that has this attribute, right? We want to identify that this point over here is faulty, and at first it might appear, even though this looks visually away from this kind of a heat map, if you were to look at any one of the axes alone, it looks pretty normal, right? Just from the heat tolerance point of view, it's kind of in the close to the mean, and if you just look at the power output, it's also kind of near the mean. But it's this combination that makes it kind of an anomalous example, right? And the way this kind of an anomaly detection can be carried out in practice is to construct a density estimate P of x for these points, where this P of x assigns high probability for anything that falls in this region, and P of x assigns low probability for anything outside this region, right? And a common approach to doing this kind of a density estimation is to use mixture of Gaussians, right? And the way we go about doing mixture of Gaussians is, so first what we are going to do is to provide you an algorithm to do mixture of Gaussians, and we're going to construct this first algorithm based purely on intuition, and then what we're going to do is describe this general framework called expectation maximization, and then rederive the Gaussian mixture model using this framework, and see that we end up with the same algorithm that we got using intuition. The expectation maximization that we're going to see next is a more general framework that works for a broad class of generative models. These are examples of generative models, and the Gaussian mixture model is just one such model which can be solved through expectation maximization. This question?
So even given that we know we have to fit Gaussians, and you said we will typically choose k like based on just trying out different k values and seeing if there's but shouldn't we also doesn't someone need to tell us what is the highest what is the upper bound for the frequency that we will tolerate on the PDF, because the k will fit best as k approaches the number of data points, right?
Yeah.
So don't we need to be told what the frequency of the PDF is maximum?
So the question is, I guess, to kind of summarize this, how do we find out k? And it is true that as we increase the number k, we kind of fit the data better and better. And in order to kind of think of what's the best value of k, I will leave this as a thought exercise for now, and we'll come back to this probably next week. Try to see how you can apply, what we learned in learning theory, bias and variance. How can you, give some thought on how you can apply bias variance analysis on this kind of a problem, right? We'll come back to this later. For now, we'll, for today and for the rest of this week, we're going to just cover more algorithms, and we'll, come back to it later, with, and see how we can kind of approach it in a more principled way. For now, as a mental exercise, see how you can apply bias variance analysis in this kind of a setting. Right. So, in the mixture of Gaussians, or Gaussian mixture model, so we are given a training set of just x's, right? And then we're going to assume there is this zi which belongs to a multinomial distribution with parameter phi, where phi j is greater than or equal to 0 and the sum overall j equals 1 through k, phi j equals 1. Right? And phi j is basically phi j is the probability that zi equals j. Right? And then we have xi given zi equals j to be distributed from a normal distribution of mean mu j and covariance sigma j. Right? So this is describing the model. So the way we assume the model works is that first we sample the class identity z from some kind of a multinomial distribution, right? And then once we have sampled the identity, we generate an observation x condition on the z value that we sample from some particular Gaussian distribution with mean mu j and covariance sigma j. This is very similar to GDA. Right? In GDA, the differences between this and GDA is that in GDA we call z as y, here we are just calling it z, and that is a common pattern that you will see when in the algorithms where we are doing full observation, which becomes a supervised setting. The variables that we call y, we end up calling them as z in unsupervised setting because they are not observed. Right? In this case, there is this underlying z that we do not observe, that is sampled from some multinomial distribution, and depending on the identity of the cluster that we sample, the observation is then sampled from a corresponding Gaussian distribution that has a mean and covariance specific to that cluster. Right? In these cases, zi's, because they are not observed, are called latent variables. So a latent variable is a fancy name for a random variable that we have not observed. We have just not seen what its value is, and that's why we call it latent. Yes, question?
So is the phi the class probability?
So phi over here is you can think of it as the class prior, the class prior that we had in GDA. This just tells us of all the examples x's that we have, what fraction of them belong to cluster J. Good question. And now in GDA, we performed maximum likelihood estimation in GDA, and our maximum likelihood objective was in GDA it was log p of x comma y, where mu, sigma and phi were the parameters. Right? So this was the log likelihood objective in GDA. Right? Whereas in Gaussian mixture model, we do not observe y. Right? And so in the Gaussian mixture model, our objective will be to maximize log p of x given for phi, mu, sigma, and this will be our likelihood function. Right? That's the only difference. Over here, the objective was the full joint distribution. Over here, we would have liked to do the same, but we haven't observed the corresponding y's, which we call as z's here. Right? They're not observed, so we cannot construct a likelihood function because we won't know what value of z to plug in this expression. Right? If you had observed them, it was pretty straightforward. We would have been just doing GDA. And so instead, what we do is maximize log p of x, right? And log p of x can also be written as log sum over z p of x comma z phi mu sigma. Right? So we write out the full joint distribution and marginalize out the latent variable. Any questions how we went from this to this? This question?
I'm just not clear why we have factors like Z into our actual generator model. Shouldn't Z also contribute to the likelihood?
So the question is, shouldn't Z also contribute to our likelihood objective? And the answer is, if we had observed Z, then yes, it should have, but we don't know what Z is, so it cannot.
But you're making the assumption that we know how many total classes are there, and then given a class we are generating models. So once we assume that we are given a class, then it should start factoring.
So the question is, we are assuming there are k clusters, and given a setting, some value for k, shouldn't we therefore account for the cluster identity? We are making an assumption about k, but we don't know which of those k clusters each point belongs to. Okay. Right? So our objective is to now maximize this expression, which is the same as this expression. Right? And for the rest of today's lecture and throughout, it can be useful to set up some kind of terminology. So for example, P of Z, we will call it class prior, or in cases where Z is not discrete but it's continuous, we'll just call it prior. Right? P of x comma Z, we will call it the model, because it describes the full data generating process. The joint distribution always describes the full data generating process, and that's always called the model. Right? And Z in unsupervised settings is called latent, because we don't observe it. Latent is just a fancy word for unobserved. Okay? And P of Z given x, we will call it the posterior. Right? And finally P of x. So P of Z is called the prior, and P of x will be called the evidence. Evidence because x is what we observe, that's the evidence based on which we are performing inference. Right? This is just terminology, and this terminology is pretty standard and used in many papers, many books. So our goal is to maximize the likelihood using the evidence. Right? And this the way we go about doing that is right. So to directly maximize this evidence, directly maximizing this likelihood, if we were to attempt it the way we did it with GDA, of taking derivatives, setting it equal to 0 and solving for the parameters, you will observe that you won't get a closed form expression for this. You can try it out, you won't get a closed form expression for the way we got it with GDA. In GDA we got a closed form expression because we had observed both x's and z's, we called it y's, and if we had observed both the x's and y's here, we would have gotten a closed form expression, but because the z's are not observed and we are taking this, marginalizing them, if you work it up, we will not get closed form expressions. So instead what we will do is, just like taking inspiration from k-means, we are going to first imagine or come up with some kind of an estimate for zi's first. So the algorithm that we are going to do is repeat until convergence. where this is just taken inspired by k-means. We'll call it the E step. For each I comma j, set W I j to be equal to P of Zi equals j given xi, parameters phi, mu, sigma, and the L step where we update the parameters phi j equals 1 over n I equals 1 to n W I j. Mu j is sum over I equals 1 to n W I j xi over I equals 1 to n W I j, and sigma j is equal to sum over I equals 1 to n W I j xi minus mu j xi minus mu j transpose divided by I equals 1 to n W I j. So what we did is we start with some random initialization. So randomly initialize parameters, and so the repeat will start after we randomly initialize it. Randomly initialize mu, phi, and sigma. Right? Start with some random initialization and think of this as the way we randomly initialize the cluster centroids and k-means. Right? And based on the random initialization, in k-means, for each point we associated it to the nearest cluster centroid. Right? And the kind of similar operation that we are going to do here is for each point we are going to assign a weight to each cluster centroid specific to that point, where the weight is the posterior distribution of P of z given x. Right? So given a point, we calculate a posterior distribution of the probability that this point belongs to a particular centroid, and this is just the posterior distribution. We're going to call it a weight. And once we calculate this weight, we're going to reweight all our data points to calculate the corresponding mu's and sigmas. Right? So for example, xi will will have a weight of, let's say, if there are say 3 centroids where k equals 3, then P of z I equals j given xi. Right? This could be some kind of multinomial distribution like 0.1, 0.7, 0.2, right, where this belongs to k equals 1, k equals 2, k equals 3, where if the centroid mu was close to mu2 was close to xi, then it would have a higher weight, and these two are farther away, so it has a lower weight. In case of k-means, we would do a hard assignment of every point to one cluster only, but over here we are doing a soft assignment where every point has a soft assignment in the form of this probability distribution for all the cluster centroids. and the probability assigned to the centroid that is closer to the point. By closer here we mean in a probabilistic sense, where it is it has a high likelihood in that cluster's Gaussian distribution, then it will have a high posterior probability. And we do this kind of a soft assignment of every point to the set of all clusters. And using the calculated weights, we recalculate the mu's and sigmas using the weighted data set. Here every point I contributes to every centroid j, and the contribution is weighted by the corresponding wij. Questions?
So that first step, the E step, yeah. So that will have. So will that have like a closed form expression where you calculate all the distances and then divide by the sum of all the.
Yeah. So the question is, will this have a closed form expression?
It's just that, right? Like what you wrote on the right. It will be 0.7 over 0.7.
Yeah. Yeah. So the question is, so for this I would remind you, in case of GDA, we had calculated a posterior that was very similar, and if you remember, the posterior had a form of it had the form of a logistic regression. In that case, however, we limited ourselves to two points, to two classes, and we also had a constraint that sigma was common to all of them. But in this case, when we relax that constraint, what we will observe is that the posterior takes the form of a softmax. Right? It takes the form of a softmax that uses quadratic features of x's. Right? But for a fixed value of, for small case, you can come up with an expression for this, and in fact you'll be doing this in your homework, so that will be clarified in your homework as well. Right? So inspired by k-means, here is a version of, you can think of the Gaussian mixture model as soft k-means. People call it the soft k-means as well. We call it soft because in the assignment phase, in k-means, right? In k-means, it was a hard assignment. Right? This corresponds to the E step. In k-means, the cluster identity was a hard assignment. You can think of k-means as a way in which we calculate a posterior distribution, which is always one hot. Right? If we calculate these kind of posterior distributions, then we effectively get k-means out of GMMs. Right? And in the equivalent of the M step was the way in which we were recalculating mu's. The mu j's, we used only those x's for which the cluster identity matched the corresponding cluster. And over here, instead of having an indicator function, we are going to use this soft assignment weight. Yeah. Any questions?
So just when the w's are binary, then it becomes k.
Yeah. So if w's are one hot, then this will essentially be k-means. Yes, question?
The WIJs, how do we calculate them if we haven't observed ZI?
So the question is, how do we calculate wij if we have not observed zi's, the z's? Is that a question? Yeah. So here, in order to calculate this, we don't need to know zi's. Right? So we don't need to. So we are just constructing the probability that zi could be equal to j. Right? And the way we go about doing this is to use the Bayes rule. Right? And the way you use the Bayes rule, right? So, and this can be calculated as p of, so p of z given x is equal to p of x given z times p of z over sum over all z p of x given z times p of z. Right? Over here, p of x given z is normal distribution. So this is Gaussian. Right? And p of z is just multinomial. right? And in the denominator, it is the same terms, Gaussian and the multinomial, but you sum it over all the classes. And you will see that just the way you showed it in homework 1 for GDA, where in GDA this took the form of a logistic regression. Here you can actually show that it takes the form of a softmax. It's very similar calculation. Any questions? Right? Yeah, so this is basically the Gaussian mixture model where we derive the steps to be by taking inspiration from k-means, right? And we are intentionally giving it the names the E step and the M step, because next we are going to talk about the EM algorithm, and we're going to derive it in a more principled way, and we're going to end up with the same update rules, right? And this is, think of this as soft k-means. Soft k-means. Right. Okay, now we're going to switch gears and talk about the EM algorithm. So the EM algorithm is also called the expectation maximization algorithm. That's an algorithm where it gives us a framework of performing maximum likelihood estimation when some variables are unobserved. Right? It is used in cases where we have a functional form for the joint P of x comma z, and x and z could be anything, but z's are not observed. So expectation maximization. Right? Expectation maximization is an algorithm where we perform MLE in the presence of latent variables. Right? So where the true model is P of x comma z with some parameters theta, and if we observe x and z jointly, if everything is observed, then the problem is very simple. We perform simple maximum likelihood estimation, but when z is unobserved, we want to instead perform maximization of the objective L theta equals log P of x, where z is marginalized. And the EM algorithm or the EM framework gives us a framework for achieving this, where we maximize log P of x in an indirect way rather than directly taking the derivatives and setting them to 0 and so on. Now, before we go into the EM algorithm, some kind of it can be useful to have some kind of a context here. So the EM algorithm was discovered sometime in the, I think, early 1970s, where where people were trying to perform MLE in the presence of unobserved data, and it so happens that this framework is so general and so powerful that it has been adapted in so many different ways, and it has been minor extensions to the EM algorithms are there in so many different forms. But this framework is somewhat central, and understanding EM in a deep way will be extremely useful if you are interested in things like deep generative models. Right? So over the last few years, there has been tremendous growth in deep generative models, where you might have heard of variational autoencoders, generative adversarial networks or GANs, or flow-based models, GLOW-based models, and all of them, understanding all of them would be much easier if you really understand the EM algorithm well, because the EM framework gives you a kind of a mind map where you can place all these different algorithms and kind of understand their strengths and weaknesses and what's common between them, what's different between them, and so on. So EM algorithm is one of the key algorithms to for even modern deep learning or deep generative models. Right. So before we jump into EM algorithm, we're going to first look at something called as Jensen's inequality. So Jensen's inequality is a very general probabilistic inequality that's used in very many places in probability theory and applied probability theory, and it will show up in our derivation of EM algorithm as well. So you can think of Jensen's inequality as a probabilistic tool that we will use in deriving EM. But Jensen's inequality by itself is a very generic and commonly used inequality in probability theory. So let's assume a function f to be convex. Right? Assume f to be a convex function, which means f double prime of x is greater than equal to 0 for all x. Right? And we say that f is strictly convex if f double prime of x is greater than 0 for all x. Right? So the mental picture to have is f of x, and this is x. F of x and x. So this is an example of a convex function. Convex functions are bowl-shaped functions, right? And they can have a 0 second derivative in a few places where f prime of x is greater than or equal to 0. But in a strictly convex function, the second derivative is never exactly equal to 0. It's always greater than 0. So if there are straight lines for certain input ranges in your functions, then it can still be convex. But for a strictly convex function, there cannot be straight lines. Right? It should always be curving upwards. Right? Now, the Jensen's inequality tells us that expectation of f of x, where x is some random variable, is always greater than or equal to f of expectation of x, where f is convex. So this is Jensen's inequality. So the Jensen's inequality tells that the expectation of f of x, where f is a convex function and x is a random variable, and the expectation is taken with respect to the randomness in x, will always be greater than equal to f of the expectation of x. Right? And moreover, if f is strictly convex, then expectation of f of x equals f if then if expectation f of x equals f of e of x, then x equals expectation of x with probability 1. Right. There's a lot of jargon here. We'll dissect it in a moment. So just to restate it again, Jensen's inequality says if f is a convex function and x is any random variable, then expectation of f of x is greater than equal to f of expectation of x. And moreover, if f is strictly convex, then this statement holds true. And this statement holds true only if f is strictly convex. Now, if the statement is if f of x equals expectation of f of x equals f of expectation of x, then it must be the case that x equals expectation of x with probability 1, which means essentially x is a constant. Right? Now, what does this mean? To kind of understand this more intuitively, this picture can help. Right? So let this be some function f of x, right? And this is basically x, right? And use a different color here. Let's also assume that x has a probability distribution associated with it, right? So the green dotted line represents the probability density of the random variable x, and f is some function of x. Right? Now, expectation of x or would be somewhere here. So let's call this expectation of x. Right? So expectation of x is so think of it as like the mu if this is a Gaussian. Right? That's the expectation of the random variable. Right? And now f of expectation of x. So in the case where x, let's assume x takes only two possible values. So let's assume let's draw another picture here. So this is x, this is f of x. Let's assume x takes only two possible values. Let's assume it's a discrete distribution. Here here x was continuous, but to understand Jensen's inequality, let's assume a discrete setting where x takes only two possible values, this value and this value. Maybe they are 0, 1, 2, 3, 4, and 10. Let's assume x takes any one of these values, and the mean of x, if it takes with probability half the value 1 and with probability half the value 10, then expectation of x will be 5.5. Right? So expectation of x equals 5.5. It's 5.5? Yeah, 5.5. And this over here is f of expectation of x. Right? Does that make sense? This is the expectation of x. You evaluate f at expectation of x, and you get f of expectation of x. That's the right hand side. Right? Now, similarly, with probability half, f of x takes this value, and with probability half, another half, f of x takes this value. Right? So this is, let's call this a and b. So this is f of a, and this is f of b. Right? And expectation of f of a and f of b is basically the midpoint between f of a and f of b. Right? Because with probability half it takes this value, with probability half it takes this value. So the expectation of f of x is this one, right? And this is expectation of f of x, right? And it so happens that this point will always be the midpoint of the chord connecting f of a and f of b, right? And what Jensen's inequality is telling us is that this point, the point that's the midpoint of the chord connecting 2 points on f, will always be higher than this point, right? So f of expectation of x is always less than the expectation of f of x. Right? Is this clear? Can you raise your hand if you understood this? Some of you have not. Okay. Can anybody tell me what's still confusing here? I can just go over it again. So f is a convex function which is kind of bending upwards, right? And the x-axis denotes some random variable, right? And in this case, just for the purpose of understanding Jensen's inequality, let's assume x takes on two values, one of two values, either 1 or 10, with equal probability. So the expectation of x is therefore 5.5, right? That's over here. Now f of 1, let's call it a. F of a is this point. So this is f of a. So the height from the x-axis to this point, this is f of a. And similarly, if this is b, this is f of b. And the expectation of f of x is therefore the midpoint connecting these 2 points, right? And that comes over here. And the f of expectation of x, where expectation of x was 5.5, is this point that comes over here. And Jensen's inequality is therefore essentially saying that the chord connecting any 2 points of a convex function always lies above the chord itself. Right? The expectation of f of x is higher than f of expectation of x. Right? Kind of understood? All right. Okay. Let's move on. And it also tells us that if f is strictly convex, right? F is strictly convex, then f of x equals, if f is strictly convex, and if expectation of f of x equals f of expectation of x, then x equals the expectation of x itself, which means x is essentially a constant. What does that mean? So here's an example of f of x that is strictly convex, right? Now if expectation of f of x equals f of expectation of x, when can that be possible? Right? Expectation of f of x equals f of expectation of x. When can, let's assume a and b are here. Right? This is expectation of f of x, and let's say this is f of expectation of x. Right? If f is strictly convex, and if the two are equal, f of x equals expectation of x, then the only way that is possible that f of x equals expectation of f of x is if x has a probability density right. Now over here in this dotted line, essentially I'm drawing the probability density of x, which is like a Dirac delta function where it has all its mass concentrated at just one point, right? And in this case, this is expectation of x, and f of expectation of x is here. And also, because x always takes on this value with probability 1, f of x also always takes on this value with probability 1, and therefore f of x equals f of expectation of x equals expectation of f of x, because essentially the equivalent of the chord connecting 2 points has length 0 here, right? All the values of f of x are always here, and x always evaluates to the same value. Yes, question?
So question over the reduction. When x is continuous random variable, what is the expectation of a continuous function? Just like the average?
So what's the expectation of a continuous random variable? If x is a continuous random variable and it has a PDF, let's call it small p of x, right? Then expectation of x is equal to the integral of x times p of x dx.
So your p of x will become f of x, right?
So p in this case is some probability. So the green line, the green dotted line is p of x here.
My question is, what is e of f of x?
So what's e of f of x? So e of f of x, so if e of f of x is equal to the integral of f of x p of x dx. Good question. Right? So this is Jensen's inequality, and the reason why we require f to be strictly convex is because if f were not strictly convex, then you could have a case where f of x is flat in some place, and x has this density, and expectation of f of x would be here, and f of expectation would be here, and also expectation of f of x would also be the average f of x in this region, which is also a constant. So expectation of f of x would be equal to f of expectation of x, even though x is not constant, because f has a flat region somewhere. This question?
In convex case, can we always say that the x's will be distributed along the region where f double prime is 0?
So the question is, in the convex case, can we assume that?
The x's will have to be distributed where f is flat, so that the chord is like.
So for this case, yeah. So if for this to hold without x being a constant, for x to and f of x to be the same, then all of x should be distributed in a region where f is flat. Yeah, that's right. Right. So what are some examples of convex functions? Anybody example of a convex function? Y equals x square. Example for concave function? Minus x square, y equals minus x square. Yeah, yeah, that's good. So examples of convex, concave, and strict, yes or no, right? So convex function, we saw x square is convex, minus x square is therefore concave, right? And is this strictly convex? And therefore also strictly concave, right? Now another function, y equals or f of x equals say mx plus c, straight line, is convex. By definition it is convex. A straight line is convex and it is also concave. But is it strict? No, right? It's not. Great. Now what about e to the x? convex. Minus e to the x is therefore concave. Is it strict? What about log x?
No, yes.
So log x is concave, and therefore minus log x is convex, right? And it is strict. Right? Cool. Now, how is this useful for expectation maximization? Yes, question? Yeah, a straight line is always convex and concave because so f double prime is equal to 0, and the definition of convex is that f double prime should be greater than or equal to 0. So and it's equal to 0, so it satisfies greater than or equal to 0. And similarly for concave, it is less than or equal to 0, and it's equal to 0, so it satisfies less than or equal to 0 as well. Right? Now, so using Jensen's inequality and with these observations that expectation of f of x is greater than or equal to f of expectation of x and so on, we can adapt Jensen's inequality to the concave case, where basically it says if f is concave, right? Example, f of x equals log x, right? Then the inequality will switch. So the expectation of log x instead of greater than or equal to will be less than or equal to log expectation of x. Right? This is also Jensen's inequality. So now let's derive the EM algorithm. Right? So in the EM algorithm, our goal is to maximize log p of xi, theta, whereby theta mean all the parameters I equals 1 to n. Right? We want to maximize this. That's the goal. What we are trying to achieve. This is our end goal. We want to maximize log p of x. But however, maximizing log p of x can be hard because the z's are unobserved. If z's were observed, this was very easy, but z's are unobserved, so it's hard. Right? That's the case. That's the setting we are in. And now, for the derivation, I'm going to assume one example. So I'm just going to write it as log p of x comma theta, and I'm going to leave the summation out. But basically, the entire derivation that we are going to do, you can include the summation and everything will hold. Right? This is just to simplify notation. Right? So log p of x, we want to maximize this. That's our goal. Right? So the first thing we're going to do is write log p of x comma theta is equal to log of the sum over z p of x z theta. Right? First, we're going to marginalize out z. Right? And then once we do that, we will define some arbitrary probability distribution called q over z's, and write this as log sum over z q of z times p of x comma z theta divided by q of z, where q of z is greater than 0 for all z. Some arbitrary probability distribution over z. It could be anything whatsoever. Any kind of probability distribution over z such that q of z is greater than 0 everywhere. This question?
You said that the first thing, like the first line you wrote from the left-hand side, the goal, it's a hard problem. What does it mean to be hard? Because you could write p of c, p of x, p of c for every single example. You can solve it.
So the question is, it's why is this a hard problem?
You can solve it. P of z times P of x given z, right? And for every single z, you can make a probability distribution.
So it is hard because you're having a summation over here, right? And in general, when in the cases where z is continuous, this will be an integral, right? And that integral can be arbitrarily complex.
So you mean computationally expensive?
It can be computationally expensive. It can be analytically not possible in cases when we want an analytical solution. Right? Good question. So we come up, Q can be any distribution whatsoever as long as Q of z is greater than 0 for all z. And now we can see that this can be written as log right? What did I do here? Nothing basically. So this is the definition of expectation, right? So this is a function of z, some function of z, right? And think of this as the probability, and this is some function, and therefore this is just the expectation. Is this clear? Yeah. Okay. So this is just the expectation, and now we make use of Jensen's inequality and note that log of the expectation of something is greater than the expectation of the log of the same thing, right? And so this is going to be greater than or equal to expectation of z of q log p of x comma z theta over q of c. This question? F here is log, and log is concave. Log is concave, right? And this is our random variable x. Right? Any questions on how we went from here to here? This is probably the most crucial step. Right? All good? Okay. And this, what we see here, we will call this, give it a name. We'll call it elbow, evidence lower bound. Right? So it's the elbow of Q and elbow of x q theta. Right? And Jensen's inequality tells us that the elbow, which is defined to be this term, is always less than or equal to our objective that we want to maximize. Right? Which means now if we find thetas and q's such that we are maximizing the elbow, then implicitly for the same values of theta, log p of x is also going up. Does it make sense? Elbow is defined to be, is by Jensen's inequality, elbow is always a lower bound for log p of x, our likelihood. Both of them have theta in them, right? Now, if we find values of theta such that we are maximizing the elbow, then it necessarily means that log p of x at that value of theta is higher. And Jensen's inequality gives us that inequality. Yes, question?
Will we ever be able to take, like, let's say elbow has some capacity where it can go maximum, and then your likelihood can go till here. Will it be able to take it to its maximum?
We're going to come to that. All right. So this is the elbow, and this term elbow is something you will very commonly encounter if you're reading research papers about generative models or deep generative models. This is a widely used term, and elbow means the lesser side of the Jensen's inequality of log p of x, right? And our goal is to now, well, before we go into our goal, let's make a few more observations. Now, log p of x is greater than equal to elbow at all times. That's what Jensen's inequality says. But are there cases when log p of x is exactly equal to the elbow? Right? Are there cases? Are there cases when log p of x theta is equal to elbow of x q1 theta? And the answer is yes. It is yes because of the second part of Jensen's inequality that we saw. Right? So Jensen's inequality, we also saw that if f is strictly convex, log x is strictly convex. Right? If f is strictly convex, then expectation of f of x equals f of expectation of x if and only if x is a constant. Right? So this is one side of Jensen's inequality, this is the other side of Jensen's inequality. Right? And the two will be equal if and only if the term inside is a constant. That's what Jensen's inequality told us, because log is strictly concave. Yes, question?
What do you mean by x is a constant in this case?
In this case, we want this entire term over here to be a constant. Now, are there cases? So the next question is, are there, under what circumstances is this entire term over here always a constant? That's what we're going to answer next.
You mean like as you vary z, like it has to be independent of z and all?
It has to be independent of z. So it is constant with respect to z. Right? So the question now is, in order to make this inequality an equality, because log is strictly concave, the inequality becomes an equality if and only if p of x comma z theta over q of z equals some constant c. Right? And now this implies that, take q of z over there, q of z is equal to 1 over c times p of x comma z. Right? And we also know that because this is just a proportionality constant, we can write this as q of z is proportional to p of x comma z. So q of z is just proportional to p of x comma z, and in order to make this equal to we just use the calculate the proportional normalizing constant, that you're summing over z p of x comma z theta. Right? And this is basically p of x comma z theta divided by, when you marginalize out z, you just get p of x theta, and this is equal to p of z given x theta.
Why did you normalize with p of x?
So the question is, why did we normalize it with p of x? So because q of z is proportional to this, and in order to, and we know that this is a probability distribution, which means it has to sum up to 1. So this must the normalizing constant must necessarily be the sum of this. Was there another question? Yeah.
The denominator is a
So the denominator is this term that is summed over all possible values of z.
But if you are summing something, if you're summing a distribution to 1, isn't multivariate and hence you have to sum over x and z?
So this is a distribution over z. P of xz could be anything. X could be continuous. Right? Q of z is a distribution over z that must sum up to 1. Right? And that's proportional to P of x, x comma z. And it is proportional, and the corresponding normalizing constant must necessarily be the sum over the numerators for all possible values of z, because it must sum up to 1. Right? So when Q of z equals P of z given x, then Jensen's inequality will change into an equality. Right? Lots of moving parts, yes. So we started with log P of x, right, and wrote it out as the sum over z of the joint. And there's nothing fancy going on here, right? We are just marginalizing out the z, and then we multiply and divide it by some arbitrary distribution q, and by multiplying it and dividing it, the numerator allowed us to write it in the form of an expectation, right? And this stayed in the denominator. And once we wrote it as an expectation, we had log and the expectation, right? So initially we started with the log likelihood, and therefore we use the concave version of Jensen's inequality. So this log and this expectation are then swapped, right? And we get a greater than equal to expectation of log, right? And once we get this, this is basically Jensen's inequality, the one side and the other side of Jensen's inequality. We called the lower end of the Jensen's inequality, we just called it elbow, we just gave it a name, right? And then we use the corollary of Jensen's inequality to look for conditions when this inequality will be exactly equal to, right? And because log is strictly convex, the corollary of Jensen's inequality gives us a condition when this inequality becomes an equality, and the condition is that this term must be a constant. And then in order for this to be a constant with respect to z, it is necessarily the case that Q of z must be equal to the posterior distribution of z given x. Right? Whenever Q equals z given x at that value of theta, then Jensen's inequality becomes an equality. Right? And now, given these two, yes, question?
Please show once again why Q of z equals the first.
So why is this? All right. So we want to find the condition that P of x comma z divided by Q, this is equal to some constant, right? So now let it be equal to some unknown constant c, right? So you can take Q of z over here, right? And once you take it over here, this becomes proportional because it's some constant times, right? So now what we also know that sum over Q of z equals 1, right? Which means the sum over all of the right hand terms must be equal to c itself, right? And we divide it by c and we get exactly that. Okay, so Q of z is equal to the posterior of z given x at that value of theta. Thank you. Thanks for asking. Okay. So based on this, we write the EM algorithm, or the more general form of the EM algorithm. We call it the more general form because throughout this setting, we have not assumed any specific form for P of x and z. Right? It could be the mixture of Gaussians, it could be any algorithm. This derivation holds for any such latent variable model. All right. So that gives us the algorithm. So the EM algorithm. The EM algorithm basically tells for, so we have the E step for each I set Qi of Zi is equal to P of Zi given xi comma theta, and the M step set theta equal to argmax theta of I equal to 1 to n elbow of xi qi comma theta. Right. So what did we do? We basically get this EM algorithm where the corresponding E step is to set Q to be the posterior distribution of P of Z given x, and in the M step we set theta to be equal to the argmax of the elbow. Now why will this work? To see why this works, let's see this diagram. Now let's suppose this is theta. This is not x, this is theta, right? And this is so let's assume this is our this is log p of x theta, right? As we vary theta, log p of x gives us different values. This is not the density, this is the likelihood because the x-axis is theta and not x, right? And it's a dotted line because we don't know it, right? It is hard to calculate. We have to marginalize out x, which may be an integral. And what we got from this elbow is that for any given value of q, the elbow of x for q and theta will always be less than or equal to log p of x. That's what Jensen's inequality gave us. So Jensen's inequality tells us that, this is, write this as, right? So this is one possible elbow x comma q and theta, and let's consider another elbow, right? So for example, this is another elbow x q theta, right? So for different choices of q, we get different lower bounds of p of x, right? And what Jensen's inequality tells us is that, or the corollary tells us is that for a given value of theta, let's assume this is our randomly initialized theta of 0, right? For this value of theta, if we choose q to be p of z given x theta 0, for this choice of q, let's call it q0, right? For this choice, if supposing this is the elbow for q0, then it basically tells us that the elbow value equals log p of x at this value of theta, which means the elbow touches log p of x at this value of theta naught, right? When we are at theta naught, if we choose if we choose to construct an elbow using q as the posterior distribution with that parameter value, then the elbow will be tight with respect to the invisible goal that we are trying to maximize at that value of theta. And now if we maximize in the m step, if we choose a new theta such that we maximize right, if this is theta 1, that is the theta for the next iteration, and now we construct yet another elbow, right? Now the new elbow will be constructed using this Q1, which uses theta Q1, then this elbow will be tight at log p of x at theta 1, right? Depending on the choice of the q to be equal to the posterior using the corresponding theta value, the elbow that we'll get will be tight will be touching the log p of x. That's what Jensen's inequality's corollary tells us. Now if we start at theta naught, maximize the elbow, that is the m step, we get a new theta 1, construct a new elbow and maximize that one, and we reach here. So this will be theta 2, and here we construct yet another elbow such that it is tight at this value of theta 2, and so on. If we repeat this over and over by constructing different lower bounds at each value of theta, and we are maximizing the lower bound and so on, then we will eventually reach a local optima where the algorithm converges, which means theta stops changing. And that's essentially what the EM algorithm does. So this is the rough intuition of or the visual intuition of how the EM algorithm works. And in the next class we will go through a proof to show that it actually converges, more than just simply drawing some pictures. Yes, questions?
How do you even compute the error in that step? Like you just take the p of x comma theta over q of x?
Yes, exactly. So how do we compute the elbow? The elbow is exactly this. Exactly, yeah.
But you don't have p of x comma theta.
So in the next class we'll see an example of how we apply to Gaussian mixture models where it might be more clear. But for now, for the purpose of this lecture, it's enough to have this abstract view of how the EM algorithm works in general, and in the next class we'll apply it to Gaussian mixture models and see exactly how each of the steps work. Is there any other question? Yes, question? Is theta given as z equals theta transpose x?
That's how theta is defined.
Now theta here is some unknown parameter of the model. No, we don't make any linearity assumptions.